Hi, and welcome to 7.3 Circular Motion Practice. As you could see, there are plenty of multiple choice problems for you to practice with. I recommend you try them on your own, as with all my videos, before watching this. And then there is even a couple short answer questions. Note, there is an answer key in the back, so if you'd like to just check your work and make sure that you're doing everything correctly, you can do so. I'm going to try to remember to circle each question number as we go through it so that you could scroll through the video and, that way you don't have to watch the whole thing if you're looking for a specific question. So I'll try to remember to do that for you. I'll circle the question in the beginning of me talking about it. So, number 1, base your answer to the following questions on the information and the diagram below. The diagram shows the top view of a 65 kilogram student at point A on an amusement park ride. The ride spins the student in a horizontal circle of radius 2.5 meters at a constant speed of 8.6 meters per second. The floor is lowered and the student remains against the wall without falling to the floor. If you've never been on a ride before like this, I highly recommend it. It's a lot of fun. Do it before you get old and throw up from going on rides like this. So number 1, which vector best represents the direction of the centripetal acceleration of the student at point A? Again, when they're looking for the direction and it says centripetal acceleration or centripetal force, the term centripetal should be a key word for you. It comes from the Latin centripetal. This means center, and then petere means to seek. All right, so that means a center-seeking acceleration or a center-seeking force. So at point A, the centripetal acceleration points towards the center of the circle. That's basically all it's saying. The centripetal is always towards the center. So at A, towards the center means choice A. See how the vectors are pointing in the same direction? All right, number 2. The magnitude of the centripetal force acting on the student is approximately what? Now they tell you the radius is 2.5 meters, and they tell you the mass is 65 kilograms, and they even tell you the speed or the tangential velocities. Remember, speed is just the magnitude of the velocity. That's 8.6 meters per second. They're asking for the centripetal force. Your reference table has a equation for centripetal force. F is equal to ma. Fc is equal to mac. It's basically Newton's second law for circular motion. So we're looking for the force, and we have the mass, but we don't have the acceleration. So if you wanted to use this formula, first you'd have to find the acceleration. It's equal to v squared over r. So the acceleration is equal to 8.6 squared divided by the radius, 2.5, which is 29.584, 29.6. And I'm just realizing that I didn't circle number 2. So sorry, I started number 2 already if you scrolled to this. I'm going to try to remember better. Let's see. So now we found the acceleration first, and the mass is 65 kilograms. The acceleration is 29.6. So the centripetal force is 1,924 newtons. Okay, so you get this nice answer, and then you look at your answer choices, and it doesn't really look like your answer. So your first instinct might be, did I do something wrong? You did not do anything wrong. They're giving you your answer choices in scientific notation, so you just have to convert your answer into scientific notation. Here's the decimal point. You want to move it 1, 2, 3 places to the left, so that leaves you with 1.9 times 10 to the third newtons. Choice B. As an alternative, instead of doing 2 equations, you could derive your own equation here. You do the same thing, but anytime you put acceleration, you're just we know the acceleration is equal to v squared over r. So why not plug in v squared over r? And now we have an equation that has all of our given information here. We're looking for the mass, we have the mass. We're looking for the velocity, we have the velocity. We're looking for the radius. We have the radius. So we can just calculate the centripetal force using this new equation. But, I try to use the equations that they give you on the reference table just so, you were still working with the same stuff. But if I was doing this myself, I would use this version because it's a little bit easier and I'm lazy. So, number 3. A 0.5 kilogram object moves in a horizontal circular path with a radius of 0.25 meters at a constant speed of 4 meters per second. What is the magnitudes of the object's acceleration? So they tell you the mass. Since they're asking for the acceleration, that's irrelevant. The radius is 0.25 meters, and the speed, or the tangential velocity, is 4 meters per second. They're looking for the acceleration, which is equal to v squared divided by the radius. The acceleration is equal to 4 squared divided by 0.25, and you get an answer of 64 meters per second squared, choice D. Number 4. A 2 times 10 to the third kilogram car travels at a constant speed of 12 meters per second around a circular curve of radius 30 meters. What is the magnitude of the centripetal acceleration of the car as it goes around the curve? So again, they tell you the mass. You don't care about the mass because you're looking for the acceleration. Ooh, I'm really tempted to skip the guess method here, but I don't want to get points off for units. So maybe that's why you guys don't write the units. Is it like you're just excited to do physics and you just get right into it? I don't know, maybe. Write the speed. The v is equal to 12 meters per second. The radius is 30 meters. If you really don't want to waste your time writing the mass, in this case you don't have to because you don't need the mass to find the acceleration in this case. So this is that, that's that. The centripetal acceleration is 4.8 meters per second squared. Choice B. Moving on, number 5. The diagram below represents a 0.4 kilogram stone attached to a string. The stone is moved at a constant speed of 4 meters per second in a horizontal circle having a radius of 0.8 meters. The magnitude of the centripetal acceleration of the stone is, alright, it's nice. They put all the stuff for you here. Technically, you have to rewrite it. So AC is equal to V squared over R is equal to 4 meters per second squared, the whole thing squared. The units are meters per second, divided by 0.8 meters. So you thought I was going to forget the units. I didn't. 4 squared divided by 0.8. That's 20 meters per second squared. Choice D. Number 6. A car rounds a horizontal curve of constant radius at a constant speed. Which diagram best represents the directions of both the car's velocity and the acceleration? It doesn't say if it's going clockwise or counterclockwise, but as you could see from your choices, that doesn't really matter. So the acceleration, it's the centripetal acceleration. It always points towards the center of the circle. So here, the acceleration is not pointing towards the center. It cannot be A. Here, the acceleration is pointing towards the center. Maybe it's C. Maybe it's B. This is not even close to pointing towards the center. It's pointing away from the center. It cannot be D. So far, we like B and C because the acceleration vector is pointing in the right direction. Now, the velocity acts tangent to the circle. In this case, the velocity is not tangent to the circle. Tangent means it only touches the circle at one point. And if we extend the circle, and if we extend this velocity vector, as you could see, it touches the circle at 2 points. That is not tangent. That cannot be the tangential velocity. This is tangent to the circle. So not only is the acceleration pointing towards the center, which it should, the velocity is tangent to the circle, which we also like. So I would say 6 is C. I just circled 6. So if you skip to 6, rewind it a little bit because I just finished it. All right, number 7. An unbalanced force of 40 newtons keeps a 5 kilogram object traveling in a circle of radius 2 meters. What is the speed of the object? Interesting. So the force is 40 newtons. The mass is 5 kilograms. The radius is 2 meters. They're looking for the speed or the tangential velocity of the object. So for me, I would do Fc is equal to mv squared over r, and then plug. We know all those things except for the velocity, so we could plug it in right to that. But that's not in your reference table. You can totally use that equation because this quantity v squared over r is a. V squared over r is equal to AC. So you could totally use this equation here and you just do it in one step. I'm going to do it a little bit longer just because if you're struggling with this one, maybe you're looking at the equations and it's not really making sense based on the equations on the reference table. But there is a way to do it, and I'm going to show it to you right now. All right, so we want to try to do F is equal to MA, but as you could see, we don't know what the A is. We have M and we have F even. All right, but we don't know what A is. Oh, actually, let me take that back. We have to do that first, right? We have to do this equation first. Why do we have to do this equation first? Because we want to get to the point where we could do AC is equal to V squared over R so that we could solve for V. See, let's solve for A first and then plug it in over here. Again, I would just do this equation, but it's not on your reference table. So this is 40, the force is 40, the mass is 5, the acceleration is actually what we're looking for first. So the acceleration is going to be 8 meters per second squared. And now we could plug that in to this equation. So the acceleration is 8, the velocity is what we're looking for, and the radius is 2. So you get v squared is equal to 16. The velocity is equal to 4 meters per second. You could have done, so this was the first step, this is the second step. You could have done it in just one step if you had done this equation, but in case you forget that or you're not sure about that one, these two equations are on your reference table. Okay, so number 8. A 1,750 kilogram car travels at a constant speed of 15 meters per second around a horizontal circular track with a radius of 45 meters. The magnitude of the centripetal force acting on the car is. So they have the mass, they have the speed, which is the tangential velocity. The radius is 45 meters. Again, I apologize, my V's sometimes look like R's. This is supposed to be an R. They're asking for the force. Okay, well, we want to do F is equal to MA. But we don't know what the acceleration is. So we could calculate that first. Or, again, we could just use this equation in one step. AC is equal to 15 squared divided by the radius, which is 45. So the centripetal acceleration is 5 meters per second squared. So the force is what we're looking for. The mass is 1750, and we just found the acceleration is 5. So the centripetal force is 8,750 newtons. Again, for me, the easier way would have been just plug it in that version of the equation instead of doing the two equations. But in case you forget this version, you could have those two on the reference table. Okay. Number 9. Base your answer to the following questions on the information and diagram below. The diagram shows a student seated on a rotating circular platform holding a 2 kilogram block with a spring scale. The spring scales read force. The block is 1.2 meters from the center of the platform. The block has a constant speed of 8 meters per second. And they label all these things right here on the diagram, which is nice. Which statement best describes the block's movement as the platform rotates? Its velocity is directed tangent to the circular path. That's good. With an inward acceleration, yeah, towards the center of the circle. I like that. Its velocity is, so this is good so far. Its velocity is directed tangent to the circular path. That's good, except then it says an outward acceleration. Outward acceleration, no way. All right, the acceleration has to point towards the center of the circle. and the velocity is tangent to the circle. Its velocity is directed perpendicular to the circular path. No way. But at least it does say it's an inward acceleration, which is the correct option. But the perpendicular, no way for the velocity. Its velocity is directed perpendicular, nope. With an outward acceleration, nope. We wanted tangent velocity, inward acceleration. It's choice A. 10. The reading on the spring scale is approximately what? So you really had to know what a spring scale is. Spring scales are a way to measure force. And in this case, the force is like tension in the string, and actually in the spring, it's holding it in. So how much force is acting along this vector here? So let's see. They tell you everything right here. So the velocity is 8 meters per second. The mass is 2 kilograms. And the radius is 1.2 meters. What is the force? I would do Fc is equal to ma, but you need to know what A is first. A is equal to v squared over r. The centripetal acceleration is 8 squared divided by 1.2, which is 53.3 repeating meters per second squared. So now we could plug this acceleration in over here. We're looking for the centripetal force, where the force being read out by the spring scale. And you just double the acceleration that we just found. So you get 106.6 repeating newtons. And they say approximately, so in the answer choice, of course, there's no 106, so you got to pick the closest thing. 110 is close to that. That they're using like some significant figures there, so they rounded it to 110 newtons. Again, personally, I would have saved some time and just used this version of the formula, because remember, v squared over r is just a. So this version, even though it looks different, is just ma still. Ma. It's the same thing. All right, so that would be a little quicker instead of doing two equations. And I forgot to circle number 10. If you skip to number 10, rewind your video. I forgot to circle it. All right, we're skipping to number 11 here. The magnitude of the centripetal force acting on an object traveling in a horizontal circular path will decrease if the radius of the path is increased, if the mass of the object is increased, the direction of the motion of the object is reversed, or the speed of the object is increased. All right, so they're talking about force. Whenever you see a question like this, you want to find an equation that relates the two physical quantities together. And in this case, it's tough because, they're asking about the centripetal force. What's the relationship between centripetal force and the radius? So you have to find one equation with that. What's the centripetal force and the mass? What's the relation there? Is there a relationship between the centripetal force and the direction of the motion? And then what's the relationship between centripetal force and the speed? There's equations for most of those options. Actually, I could tell you right now, there's no equation that has to do with the direction of the object. I mean, it could be moving clockwise or counterclockwise. That's not going to change the magnitude of the centripetal force. Doesn't even change the direction of it because it's always in towards the center. So we have our two equations. F is equal to ma. But in the first case, we want a relationship between the radius and the centripetal force. So our next equation is A is equal to v squared over r. Well, as you could see from this equation, the acceleration is inversely proportional to the radius. So as the radius increases, the acceleration will decrease. And from our top equation here, the acceleration is directly proportional to the force. So if the radius increases, the acceleration will decrease, causing the force to decrease. That's kind of a doozy. It's like a little bit of a jump. It's easier to think about if you could find an equation that relates the two quantities together, the force and the radius. But this doesn't have radius in it. So I would think of it this way. This might make it a little bit easier. Remember, we've been talking about this version of the formula for the past few questions. So now it's easier to see that this is inversely related. So we want the force to decrease. If the radius increases, the centripetal force will decrease. As we said before, if the radius increases, this decreases, therefore this decreases. And that's what they're looking for. So I would say choice A. I know there's a lot of circles there. Let me get some of the circles out of there. A is the correct choice. Now we're looking for, just to verify, like you can move on right now if you're in a time crunch, but for now, let's see what the other relationships are. Between centripetal force and mass, we can see this equation here. Right here, the mass is directly proportional to the force. So if the mass increases, the force will increase, but we wanted the force to decrease. So the mass is increasing, the force will also increase. It's not going to decrease like the question's asking. So it cannot be B. Nope. We already said, I mean, look at these two equations here. Do you see any variable that represents the direction? Nope, that's out. And then the speed of the object is increasing. What happens to force if you increase the speed? We're going to look, let's start by looking at this equation here, just so we could see. Here's the speed, here's the tangential velocity. How is that being related to the centripetal force? Not only is it direct, I mean, it's not direct. It's exponential. It's v squared. So if you increase the velocity, the force will exponentially increase. It's going to increase a lot. But we wanted the force to decrease, so it cannot be choice D either. All right, so the correct answer would be choice A. That was a good one. Number 12. Centripetal force Fc acts on a car going around a curve. If the speed of the car were twice as great, the magnitude of the centripetal force necessary to keep the car moving in the same path would be. All right, so the speed is double. So we want an equation that relates the two. The centripetal force is equal to the mass times the acceleration, but the acceleration is equal to v squared over r. So we want the velocity and the force. We want a relationship between those two. So anytime we see an acceleration, we're going to plug in v squared over r. And that's our equivalent equation there. So let me rewrite this so I give myself a little bit more space here. So this is v like that. We're doubling the speed. We're doubling the velocity. Velocity is squared in this equation. So you have a 2 squared. So 2 squared is 4. It's an exponential relationship. If you double the velocity, it's exponential. It's going to be 2 squared, 4 times Fc. Choice D. If you're really stuck in a rut, you could try plugging in just random numbers and seeing what the relationship is yourself. But it is beneficial to really memorize these relationships: direct relationship, exponential, inverse, and knowing how to manipulate these quantities and seeing what the relationship looks like. All right, number 13. A stone on the end. So number 13, did I circle the other one? Yes. Number 13, a stone on the end of the string is whirled clockwise at a constant speed in a horizontal circle as shown in the diagram below. Which pair of arrows best represents the directions of the stone's velocity and acceleration at the position shown? So we can predict it's going in this direction. So at the instant shown, the velocity vector points tangent to the circle in the direction of the motion. So we would expect a velocity vector pointing down. And the acceleration always acts towards the center of the circle. So we would expect an acceleration pointing to the left. So for A, the velocity is down. That's good. but the acceleration is down. That is not good. I'll leave it like that. So this can't be like that. The velocity for B is to the left. That's no good. But the acceleration is down. That's also no good. We wanted the acceleration to the left. For for C, the velocity is down. So that's good. But the acceleration is to the right. That's not pointing in towards the center of the circle. That's pointing this way. That's pointing away from the center of the circle. The velocity for D is down, so that's good. And the acceleration is to the left. So that's good too. That's what we have on our diagram. That's what we predicted. So it would be choice D. Number 14. The centripetal force acting on the space shuttle as it orbits Earth is equal to the shuttle's... Is this about a space shuttle? No? Alright, it's just referencing some space shuttle. Maybe it's the International Space... That's not a space shuttle. Anyway, maybe it's Soyuz or something like that. Okay, it's orbiting Earth. The centripetal force... Okay, back on track here. Here's Earth, and it's in orbit. Why is this thing in orbit? It's not because it's attached to Earth with a string. It's not tension in a string. It's gravitational force pulling it in towards the center of the circle. So the gravitational force in this case acts as the centripetal force. The centripetal force is the gravitational force. So that's the weight. Fg. Boom. 15. A ball attached to a string is moved at constant speed in a horizontal circular path. A target is located near the path of the ball, as shown in the diagram. So here's the target. At which point along the ball's path should the string be released if the ball is to hit the target? Remember, velocity acts tangent to the circle. That's not going to hit the target. That's pointing towards the target. You missed it. You're really bad at this game. All right, no, it's choice B. It's going towards the target. If this diagram's kind of hard to see, I recommend taking a piece of paper or something straight and just holding it up against your circle so it's tangent to the circle. And if you hold it at this position here, you'll see that it's pointing towards the target. And if you put it tangent to the circle here, your paper's not pointing towards the target. Here, your paper's not pointing towards the target. And here, it's not pointing towards the target. You might trick yourself and be like, oh, this is kind of close. Maybe you got close. No, remember, the vector is pointing to the left, not to the right. So it's definitely going to be choice B. Okay. Number 16. A go-kart travels around a flat, horizontal circular track with a radius of 25 meters. The mass of the go-kart is 200 kilograms. The magnitude of the centripetal force is 1,200 newtons. Oh, no, that's the magnitude of the maximum centripetal force exerted by the track on the go-kart. Yeah. What is the maximum speed the 200 kilogram go-kart can travel without sliding off the track? You do not want to exceed this force. Otherwise, you'll start sliding off the track because that's equal to the frictional force. All right, just so you know. So you can't exceed this frictional force here. So we're looking for speed, velocity. I would get used to using this equation. Fc is equal to mv squared over r. It's basically this plugged in right over here, so it's one step. So we know this can't exceed 1,200. The mass is 200. The velocity is what we're looking for. And the radius is 25. So you get 30,000 is equal to 200 v squared. So v squared is equal to 150. So the velocity is equal to around 12 meters per second. Okay, number 17. If you can't picture what's going on here, this one's kind of tough at first. But this is almost conceptual. So if you could kind of picture what's going on, you could kind of see the choice right away. So A is definitely more conceptual than anything. It says which change would increase the maximum speed at which the go-kart could travel without sliding off this track. Again, the centripetal force in this case is the frictional force, the friction between the tires and the roads. So if the frictional force decreases, you're not going to be able to go as fast. If the coefficient of friction is less, let's say you put some water on the road and then freeze it, now you have an icy road, you're not going to be able to go as fast without sliding off the track because the coefficient of friction is less. Remember, FF is equal to mu Fn. So if this decreases, this decreases. And doing this kind of analysis, where you have one variable on one side of the equation and the other variable on the other side of the equation, and seeing how they're related to each other, is an important tool that you could use for a lot of other questions. Now, for these other choices, B, C, and D, they're talking more in terms of circular motion. They're talking about the radius and the mass compared to the speed or the velocity. So we want to find an equation that relates to the velocity to the radius and the velocity to the mass. And it would be nice if we could just have one equation for both things, meaning we want the velocity on one side of the equation and the radius on the other, with the mass preferably. So we know A is equal to V squared over R, and F is equal to MA. So we could plug in this term in everywhere we see an A. So that gives us this equation, mv squared over R. Let me get rid of these other two. Now we have an equation with the velocity. We're talking about the maximum speed, so we want to compare the velocity to the radius, and we want to compare the velocity to the mass. But as you can see, they're all on the same side of the equation. This equation is only useful for if we're talking about the centripetal force as compared to any of these variables. So let's solve for V so that we have V on one side of the equation and everything else is on the other side, and we could see how they're related. Is it directly related, exponential, inverse, whatever it is. So we're solving for V. So we get mv squared is equal to fc times the radius. Then you divide both sides by the mass, FCR divided by the mass, and then you get V is equal to the square root of FCR divided by the mass. That is super tiny. I'm going to rewrite it on top. So we're saying the velocity is equal to the square root of the force times the radius divided by the mass. And now we have an equation that relates the velocity to the radius and the velocity to the mass. So let's see, what happens if we decrease the radius? What happens to our velocity? Well, they're related like that. If you decrease the radius, the velocity will decrease. If you increase the radius, the velocity that you can achieve will also increase, which is what we're looking for. So that's looking good right now. Everything else so far has decreased our maximum velocity, but C is looking good. Now what happens if we increase the mass? Well, you can see they're inversely related. If we increase the mass, the velocity will decrease. So that is no good either. The answer is choice C. Okay, number 18. Which graph best represents the relationship between the magnitude of the centripetal acceleration and the speed of an object moving in the circle at constant radius? These graphs are not guessing games. Sometimes you might be able to intuitively know what graph it's supposed to be, but a good way to check yourself is always to find an equation that relates the two variables on the axes. In this case, they're talking about the centripetal acceleration and the speed, or the tangential velocity. Remember, speed is just the magnitude of the tangential velocity, the amount. All right, so we're looking for an equation that relates AC to velocity. And remember, AC is equal to V squared over R. Now, what kind of relationship exists here between the velocity and the centripetal acceleration? Is it just a direct relationship? Does it look like this? No. Remember, this square means something. It means exponential. So it's going to be choice B. All right. Oh, just kidding. Choice. Oh, yeah, choice B. All right, so this threw me off for a second. All right, see how they're like that? Hopefully that didn't trip you up either. It's this one, exponential relationship. Okay, number 19, kind of similar question. In the diagram below, S is a point on the car tire rotating at a constant rate. It's going around like this. Which graph best represents the magnitude of the centripetal acceleration of the point S as a function of time? Now it's going around the tire at a constant rate, so the velocity isn't changing and the radius of the tire isn't changing. So the acceleration isn't changing. All right, the velocity isn't changing, it's a constant rate. The radius of the tire doesn't change, so the acceleration remains constant. So this is showing an increased acceleration. This is showing a constant acceleration. It stays at the same magnitude the whole time. So that's what we're looking for. This is showing that the acceleration would decrease. Nope. This one's showing that the acceleration increases. Nope. Number 20. A satellite is moving at a constant speed in a circular orbit about Earth as shown in the diagram below. The net force acting on the satellite towards point. Remember, net force is the centripetal force. The centripetal force is the net force. All right. So the centripetal force always acts towards the center of the circle. So it's going to be choice B. Gravity is the centripetal force in this case. Gravity is pulling the satellite towards Earth, but you also have a tangential velocity. So even though it's being pulled towards the center of Earth, it's being moving in an orbital path. All right. Very good. So moving on. Number 21. Oh my gosh, we're finally at the short answer questions. Only 40 minutes into the video. Let's see. In an experiment, a 0.028 kilogram rubber stopper. So, finally we have some room. 0.028 kilograms. I'm going to write this super huge just because. A student whirls the stopper overhead in a horizontal circle with a radius of 1 meter. Just kidding, that's too big. All right, but the radius is 1 meter. And the stopper completes 10 revolutions in 10 seconds. So they're telling you the time is 10 seconds and the number of revolutions is 10 revs, 10 revolutions. It says calculate the speed of the whirling stopper. Okay. So show all work, including equation, and substitute with units, which we will do. The velocity. Well, you might be we've been doing this the whole time. AC equals V squared over R, but you don't know what the acceleration is, so you can't use this equation. That's no good. So you got to think, all right? Maybe you don't have this in your reference table, right? But this is the equation for tangential velocity. The circumference divided by the time for one circumference. It comes from this equation, which is in your reference table. We're talking about distance. The distance around a circle is the circumference. The circumference is equal to pi d. And the diameter is 2 times the radius, so sometimes you'll see it written like this. The circumference is the distance. Or well, not really the displacement, but the distance. So here is the distance traveled around the circle, and we want the time for one distance. In other words, we want the period of rotation. Now they tell you 10 seconds, but it doesn't take 10 seconds to go around the circumference one time. It takes 10 seconds to go around the circumference 10 times. So the first thing we have to do before we do this formula is find the period. And the period is equal to, by definition, the time per cycle. Or revolutions. We're calling it revolutions here. So we have 10 seconds divided by 10 revolutions. So the period is 1. What are the units for period? Well, you have a second divided by 1, nothing. So this is left in seconds, which makes sense. See how they use a capital T? That's on purpose. It's almost like the lowercase t we use for time. It's uppercase because it's a special version of time. It's time for 1 revolution, 1 circumference. So, okay, so this is equal to 2 pi times the radius, 1 meter, divided by the period, 1 second. So the velocity is 2 pi, or about 6.3 meters per second. Don't leave it in terms of pi. I mean, come on. When was the last time you were saying, oh, I ran so fast, I was running 3 pi meters per second? No. 22. Calculate the magnitude of the centripetal force on the whirling stopper. So they're looking for the centripetal force. FC is equal to MAC, but we don't know what the acceleration is. However, we know what the velocity is now, and we know the radius. So I'm tempted to say, you know what? Instead of AC, I'm going to do V squared over R. And you could totally do it that way. But since you're probably skipping to this one and you're not really sure what to do, even though we've done this a bunch of times in the previous questions, I'll do it one more time just for you. So I'm going to use, instead of making up that other equation, first, before we could do this, which is in your reference table, we have to find what the acceleration is. So you look in your reference table for a formula for the acceleration, and you have V squared over R. We have those quantities. The velocity we just found, 6.3 squared, divided by the radius, which was 1 meter. So the acceleration is 39.69 meters per second squared, which we can then plug in over here. So the centripetal force, which is what they ask for, is equal to the mass, which is 0.028 kilograms, times the acceleration. So the centripetal force is about 1.1 newtons. And that is all she wrote. Have a good day.